is Nicholas Roski here at Georgia Tech IEN. We're specifically in the bio clean room. Today, we are going to be demoing the Nanoscribe 2-photon lithography tool. This is a advanced 3D printing system, mainly printing like items on the micro and nano scale, with applications in MEMS and microfluidics, as well as optical networks. So today, we're going to be printing off a couple of structures. This system is a little unique in the fact that we print mainly with lenses. So most of the time, whenever you're thinking of 3D printers, they're going to be printing with like plastic material. This is not quite the same. So we have some stuff here prepared by the company. This solution is kind of be like a plastic material. And we only need a small droplet onto our glass slide here. So before we get into it, I have to go ahead and put in some of these lenses that we have. We have a few different ones for different size ranges, but today we're going to be using one that's on the medium scale, and that's going to be this guy here. If I can get it in the camera, there it is. This is the 25x objective lens. We have a few of them here at Georgia Tech, but today we're going to be focusing mainly on this one. But our prep is done, so that doesn't take too terribly long. Our glass slide and the objective are going to be facing each other in a way where they're going to be, like the microscope objective is going to be facing up, and our slide with the resist on is going to be kind of facing downwards. The system is printing from the bottom down, so from top down is where it's coming from, since our laser signal is going to be coming from the bottom. And we're going to go ahead and hit OK, and we're going to turn on our camera now. And right now, the system's just going through some movement spots to go ahead and calibrate where the microscope objective is. And since we are on a glass slide, we're going to be using transmission illumination. So we're going to go ahead and turn this guy on. Now we can see what's going on here. Overall, it's not too terrible, so we just go ahead and hit approach and it does all of it automatically for us. So right now, I know that we found the surface. So since we're printing on a very small scale, we look at a few things. There's a few graphs that we can look at. Mainly, we're looking at the bottom graph to see how our signal is looking. So if we see that squiggly line, that is our signal interference pattern. And that's what we're looking for. And then also it says up here in the text box, interface found with said strength. I already have a few pre-prepared samples for us to look at. So we'll go ahead and prep one of those right now. So we'll do training. And you might be able to recognize this once we start actually printing this. And we'll print off a few of these. So the way this system works, and right now it's going to start printing. And if you watch this big screen over here, you'll see it start to print. The way the system works is that there is a near infrared beam that is generated by the system. That beam is then highly focused into a very localized zone. And while it's in that zone, that is the only place where there's enough energy for this material to actually cross-link and to become a plastic-like material. So our beam is powering up. We're moving around to our start location. It's refining the interface right now. And then you can see that the beam is forming here. So right now we're printing it in sections. And you can maybe figure out what sections are what here in a second if you know Star Wars. You can see that it's printing it layer by layer. You can really see the laser slowly going through and figuring out which section is which. Yeah, there we go. So now it's pretty much completely done. And you can see that we can see the individual layers here. So each of those circular rings here, one circle, and then there's another circle, and it kind of goes down like this. We slice this thing at a resolution of 1 micron. That is a very high resolution. The overall width of this guy is around 120 by 170 in the X and Y. For reference, your hair is only around 100 microns thick. So these structures are overall very, very, very small. This allows us to make very high resolution parts, and we can also put them onto other things than just the glass slide that we had. A lot of people are going to use this to make structures that are like small coils, small lenses, and then putting them onto custom substrates, mainly for photonics work or for microfluidics and nanofluidics. Most of the time, we'll be printing small channels. If we want, I can turn on some beam controls. If I can spell control. So right now we're going to play with the laser a little bit. So overall, like in the small print that we did, you saw that the laser just kind of like activates and it goes over layer by layers, different sections. We'll print again in a second so that way you can really pay attention to how it's printing. And then you can see here, there's stitch lines. So almost anything that is really large, there's going to be lines that are stitched here, connecting the piece overall together. So that way, if you're printing over a large area, you can print it and connect it as one whole part. So I'm going to turn on the laser here, and we'll go ahead and play with this. I'm going to go ahead and move out of the way of our Millennium Falcon here. So here's the laser beam as we see it. So right now, if we have this guy moving around, you can see that there's a little bit of spaghetti forming. There's not a solid connection between the actual polymerized resin, which is that plastic-like material that is flowing away. So we can see that it's just kind of like hanging around, and we can draw with it. Of course, that's very rough, and we would never actually make a structure like this. But it's nice to see that we can actually control very specific points only where we want it to be. And that's because the near infrared beam only has enough energy at that specific point to actually cause the resin to cross-link there. Also, if we turn off the laser power too high, so if I go to like 90 or 100, we might be able to see that the bubbles start to form. So that's because the resist itself, the plastic-like gel that's in there, is actually kind of boiling away a little bit. There's a little bit of solvent that's being evaporated. So for fun, one more time, we'll go ahead and print this last Millennium Falcon. I'm going to turn off my beam here. And then my job is already loaded. So I'm just going to refine my interface. And I'm going to hit start. So here we're going to mainly focus again where it's printing. So here you can see that it's starting. And you can really see that laser starting to go like really fast. There's a few like micrometers that are adjusting the X and Y positions all in one go. There we go. And this thing prints relatively fast. If it prints, it can print this whole structure in 11 seconds if we wanted it to. But right now we have it stitching together different sections, so there's extra movement in between. But overall, I think the print time there's around 34 seconds, and that's not too long at all. Most structures that people are printing are going to be on the scale, so they're going to be able to rapidly go through and change their designs and test them, and then come back and reprint them the next day. A lot of this tool is what it's used for is for rapid iteration and for mass scale on a smaller scale. So you can print like hundreds of these devices in one go, put them onto a wafer, and you'll have hundreds of devices ready in like a matter of hours. This is especially important when you're printing needle structures for medical applications. So sometimes people are printing needles that are maybe a few hundred microns tall, and they're meant to only puncture the surface of your skin. And you're able to print like hundreds of these in the matter of like a few hours and change designs. And the other thing that's nice is this mainly looks like a 2D object. It's 3D, it's very thin, it's around 34 microns, but you can print structures like up to 8 millimeters tall. The thing that's nice is that this resist is so thick that you can pretty much print structures freestanding and without any supports, meaning that you don't have to do much post-processing or much after work when you're done with a print. But for now, that is about all we have. We can try and load up one more file and see the difference on some of these structures. So we'll go ahead and do another file here. We'll go over here and move away from these guys. There'll be another Millennium Falcon, but it's slightly different. And each time we want to do this, we have to reload the files that have all of our slicing configurations on it. But this one's printed all in one go. So instead of having things move around and shift, you can see that this one prints much faster. But thank you for attention. That's all I have for this tool.